I've been doing Erlang for quite a while. I encountered Joe's thesis, I think 9-10 years ago, and at that point I've been hooked. I also speak about space systems a lot, and the question I get is why aren't we using Erlang in space, or what would it take to use Erlang in space? So my talk today is Piecemeal into Space, and I want to try and answer that question. I want to answer what will it take to actually get Erlang into space. And I think it's important to start to understand first, what is Erlang? It's important to understand the computation model. It's important to understand the machine that Erlang is proposing. So this is a process in Erlang. This is kind of the fundamental unit of computation. A process is sequential internally, so any computation you write is sort of going through in a way that's easy to understand and predict. It has a unique name. It has a PID. You can also assign a more human-friendly name to it, and it has isolated memory. So you can't fiddle with the memory of a process from another process. You have to send messages. So this is really the first basic component of the Erlang computational model, memory separation and then fiddling with memory through message passing. And each one of these processes is responsible for interpreting these messages. So messages end up being little units of computation. Two processes interact by sending one another asynchronous messages, and they do so by sending to a name, either a PID or a human readable name. Now, if you want synchronicity, and we use synchronicity, that's not actually a primitive in the Erlang computational model. That's actually just built on top of asynchronous behavior. You simply have two processes. One sends an asynchronous message to the other, and then waits for the process that it sent a message to respond back appropriately. So that's not built into the basic language. Processes can be linked. So links are formed either by spawning automatically or by two processes that are alive, one knowing the process that it wants to link to. Links are unidirectional. So if A links to B, it does not imply that B links to A. And by default, links don't do what's called trap exits, which means if you have linked to a process, if A links to B and then B crashes, that exit will propagate back up. So you have a process here that is linked to another one. The process is crashed, the exit is not trapped, and then that process blows up as well. Now, it is actually possible to trap an exit, which is how you catch these exits, which is how you do something intelligent with them. And they end up just being asynchronous messages. So this is a situation where our friend with the dangerous link, if it should crash, it's linked safely by trapping the exit on the link to a process up at the top. And this is how supervisors work in OTP. So OTP is a set of behaviors built on top of the primitive computation model. It's not baked into the language. It's simply formed out of this fundamental computation model. And crashes end up just being messages, just normal messages that you receive and then you can act on. So it's possible for a process to link up. You can make many links from a process, and you can build increasingly complex hierarchies of processes. And these processes represent some unit of computation. They're running independently of one another. They're sending messages back and forth. And it's up to you, the programmer, to build order out of all of this. So it's a relatively limited set of primitives. Now, there's one small bit about messaging that really needs to be explained. Each process, it's hard to overstate this, is uniquely identified by a PID, and that PID encodes information about what machine it's running on. It encodes information about the individual process running on that particular machine. But you can also assign a name to a PID through this sort of global registry that all the machines that are coordinating in an Erlang system are able to understand. So here you see some process that's sending a message to a named process. Now, the neat thing about that is, should that named process die, its supervisory process can simply restart it. So the process that's sending messages doesn't need to be involved in the re-replication of a certain part of system. So if you have a defect, if you have a crash, that part of the system just comes back on, and anything that's sort of coupled to it is none the wiser. Which is fantastic, because it means that you're able to remove an entire class of state management out of certain subsections of your program. And et cetera, et cetera. You build larger and larger. These don't even have to be running on the same machine. That's sort of transparently handled for us. You can inspect that, but you don't necessarily have to. And there's really one last piece to the fundamental Erlang computational model, and that's time. So Erlang is a soft real-time system. And what that means, if you have two processes, A and B, and A wants to send a message. So in this particular case, A is a process that is sending a spin stabilization message to process B, which presumably handles firing engines or what have you. It then calculates the deviance and sleeps for a little bit. So in this diagram, A sends a message to B, calculates that it needs to sleep for 3 seconds. After 3 seconds, exactly 3 seconds, it receives a wake, it wakes up, and then it sends another message because it's done its computation. Now this is an example where the timer has returned in the exact amount of time that you would hope. So this is accidentally a firm or a hard real-time system. But Erlang doesn't guarantee that. What Erlang guarantees is that your timer will return no sooner than the deadline that you've set. So for instance, this is also a valid situation. So the process A has said, I will sleep for 3 seconds, and then after 6 seconds it wakes up and sends its message. Now, the joke about real-time systems is actually that firm and hard deadlines are based on probability. And it's up to you as the programmer of a system to sort of drive the probability of a deadline slip down. So if you have a micrometeor that shatters a bus, your computation might be interrupted past your deadline. So it's possible to build firm real-time systems in Erlang. You just sort of have to work it correctly. So the primitives are soft, but you can drive that probability in the correct way. So, out of these primitives, what qualities is it that Erlang provides? What class of problems does Erlang solve? So these we should all be pretty familiar with. The first one is fault tolerance. So, if you have a process that is managing some type of computation and it crashes, but you've given it a name, you have a process up top that catches that crash and then restarts starts a new process and assigns the same name with the same code, then anything that calls into that is none the wiser. And that's fault tolerance, and it's great. It provides soft real-time operations as a fundamental feature of the language. The sleeps, the timers, these are fundamentally built into the VM. You get concurrency, which means that the processes that run in Erlang are what are called preemptively scheduled. Every 50,000 reductions, which is effectively a function call plus some fiddle factor, a process gets switched out and a new one starts to run. If you have only one processor in machine, you can only run one process at a time. But the neat trick is, because you have memory segregation between processes, as soon as you have multiple processors, you can start to run them in parallel. And they're none the wiser. And Erlang fundamentally provides memory safety. And it doesn't provide memory safety in the way that something like Ada Spark does by denying allocations at runtime, or Rust, where it has an affine type system. What it does is it just disallows any sort of memory access pattern that isn't copying, that isn't passing a message, which is a pretty neat trick. But if you're going to try and apply Erlang in extreme situations, you really have to understand how it maps to the machine. So this is a high-level computation model, but it doesn't really reflect the basic reality of the machine. There's no mechanical sympathy to this explanation. And space systems are usually in extreme environments. So it helps to know what does Erlang, or how does Erlang do what it does. The computational model that we've been discussing above is accurate, but it doesn't really get to the core of how you're interacting with these complex machines. So if you'll recall, this is the first simplification that we showed, simply a process. But this is another more complicated simplification of what a process is. So this is the same process with a view toward its internals. So the first thing is, a process has its own allocated block of memory that sits inside of itself. So if you actually start to tear apart the beam, the VM that Erlang runs on, each process will be a C struct, and you'll see this simply referenced in there, a block of memory. The neat trick about this is every process, because they're potentially running concurrent or parallel to one another, each process is able to allocate and deallocate in its own space. So it doesn't have to reach across the VM, it doesn't have to take a lock to do it, because it is simply executing sequentially in itself. The other really neat trick about this is Erlang is a garbage collected language. And if you've ever read any papers on garbage collection and real-time systems, you know it's a problem. Real-time systems effectively mean you can't pause for an unbounded amount of time, and garbage collectors mean, hey, we're going to pause for a potentially unbounded amount of time to collect your garbage. Erlang's pretty cool because it does not have a global pool of memory, which is not strictly true. It has binary heaps and whatnot. But because processes have their own internal memory pools, they're able to do garbage collection per process, which means that if you in fact suffer a GC pause, you only suffer it in one process. The other nifty trick here is most processes in Erlang systems are relatively short-lived. So you allocate a process in the VM, it gets its own memory, it allocates some stuff, it fiddles with those allocations, and then it kills itself. You don't ever have to do a garbage collection there, you just free the entire thing at one go. And because you've achieved strict memory isolation by hiding Erlang process memory inside of the process itself, you don't have to reason about concurrent memory access patterns, which is extremely difficult if you've ever had to do it. It's just a problem that's totally solved. So, as mentioned, you have to manipulate process memory by sending messages. And when I say you, I mean you send a message to a thing and hope that it manipulates the memory in the way that you've agreed upon ahead of time. So on the left-hand side, you see the message queue. So every process has a FIFO queue. It's an unbounded queue that it receives messages into. So it's a dual lock situation. There's a lock on the receive side. If you send a message in, you take that lock, you put the message in. If you read a message out, you take a lock on the bottom and you take it back out. It's FIFO ordered, so you have to do something if you want to receive selectively. That's kind of unfortunate. So receives in Erlang are selective, so you can set a pattern for the type of thing that you want to receive, which is a pretty nifty trick. If you combine that with an unbounded queue, you run into pretty harsh situations if you have a process that's overwhelmed. Selective receive does a linear search over your queue until it hits a match. If you have a process that's programmed to selectively receive only one type of message, but it just receives random garbage from the rest of the system, which can happen if you have a bug, its message queue will fill up with random garbage, and you'll start to see latencies tick up for each one of your receives. The selective receives in Erlang are also one message at a time, which is a little bit unfortunate, because if you have to act on 10 messages, then you have to buffer them inside of yourself. But that's okay, that's not too hard to do. Erlang processes have a link to their own code, so they don't store the code in themselves. But because they have a link to code, that allows you to do nifty things where you can live update the Erlang system. So when you start to reference code, you have a pointer to a pointer that sits inside of a pool. But that means that it's possible for you to say, apply a new release into a running system. And that's just how that works, because each process sort of knows what version of the code it's pointing to and what it should be executing on. And multi-version code running is great when you realize that your deployed system has some type of bug that you can fix. It's a relatively low-frequency bug. You apply the new code, your processes restart, you get the new version of the code. If you've ever done hot code loading in a non-Erlang system, you tend to patch a binary. My favorite example of this is the Voyager 1, which is, Voyager 2, which was programmed in Fortran. It's now past the heliopause, which means it's outside of the solar system. Once it did its primary mission, they wanted to upgrade the system software, but there's no facility for doing that. So what they did was they realized that they could trigger a bug to cause the code loader inside of the Voyager computer to reference a new place inside of Voyager. So they uploaded a tiny little program. They triggered that bug. That tiny little program then pointed its satellite or its receiver back at the Earth. It received a new stream of data and then overwrote that in memory. That new stream of data happened to be a brand new program, which would allow it to study the heliopause in 15 years when it slammed into it. Erlang's a little easier to do than that. It's also safer. You can roll back. If they had screwed that up, it would be a dead spacecraft. It would be a testament to human hubris, flying outside of the solar system. And then Erlang processes, have a little bit of metadata in them. They have references to timers. They have references to links, their priority. If you didn't know, you can set Erlang process priority. It's relatively coarse-grained, but it is possible to do. So that's an individual process. And I've talked about the concurrency and parallelism of Erlang processes, but how does that work? So this is a view of a relatively small virtual machine. On the right-hand side, you see the process that we've been discussing, and the structures at the bottoms are scheduler threads. There are different types of threads running in Erlang, but we'll ignore them for this use. Scheduler threads are the things that simply run processes. They're operating system threads. Processes only run when they're in the scheduler threads dock. So if you have, say, 2 scheduler threads as you have here, and you have 4 processes, only 2 will be running at any given time. Now, that's a little bit complicated because it depends on the number of CPU cores that you have as well. If you have 2 scheduler threads but 1 CPU core, then even though you'll achieve 2 processes running concurrently, you'll only have 1 process running at any given time. And that will depend on the operating system swapping your scheduler threads in and out. And as I mentioned before, but it's worth repeating, Erlang is preemptively scheduled. So these processes run for a certain amount of time. They then get frozen, and then they get pushed up to the top and a new process runs. So this is an example of a VM where one scheduler thread is very overwhelmed. There's one scheduler thread running a process. There's one that's totally empty. And the schedulers in the beam work steal to balance the load between them so that you drive down the latency of the individual process. Because if you're the process at the top and you have to wait for all of these processes to go through, effectively, from the point of view of one of your timers, your timer will start to slip. So if you'll recall back to the situation earlier where we had a process that got its timer exact, or its sleep, excuse me, of 3 seconds, and then another process later that took 6 seconds, maybe it was at the very top of one of these scheduler thread stacks. So the VM will try to work steal, and that just means that the other scheduler threads will come through and just pop work off, and they'll start to run them. The exact algorithm that the beam uses varies a little bit from release to release, and it's not available to the Erlang programmer for manipulation. It's simply a fact of the beam. So the beam itself is optimized for a particular kind of workload. So this is messaging. One message sends "Hello, Joe" to another process. What does that actually look like in the reality of the machine? So here's a situation where the process at the leftmost sends a message to a non-running process in the rightmost scheduler thread. So it's possible to send a message to a process that isn't actually being executed by any scheduler. And so that's why there are locks on these message queues, because two threads might be running 2 processes in parallel, and they might try to send a message to the same message queue. So if we sort of zoom in on that one process, this is a process that's very overwhelmed. It's a very popular process. And this is where unbounded message queues get problematic. So we don't actually know how many messages are in this process. But if it's doing a selective receive, its latencies are going to go up. So you have to control for unbounded message queues. You have to do analysis of your system to make sure that individual processes don't get overwhelmed. If you've ever run high-scale Erlang systems, you'll have hit this problem. One particular trick is to periodically just query in your process how many messages you have, and then just drop them. You figure, okay, well, I've gotten overwhelmed. I can't process them anyway. I just drop the messages. That's a little unfortunate, but that's one way that I've seen people resolve that, and that's how I've resolved that in my own systems. Any of these processes can be supervisors, gen servers, any of the high-level constructs that we work in from day to day. None of those are actually reflected in the reality of the machine. Those are abstractions that we've built over the top of the reality of the machine. Erlang schedules self-contained units of work over operating system threads. And the manipulation of memory is done through message passing. And that's the fundamental idea. Anything else is kind of sitting over the top. It's a pretty tidy system. It's a really unique idea. executed in a way that doesn't feel onerous. So if you've ever programmed real-time systems, you probably built something a little like this, but it was much more difficult to do. So Erlang provides that method of computation to us effectively for free, but with trade-offs, in that we lack certain types of control. And the VM is a lot more complicated. For instance, you have a global binary heap for binaries that are above a certain size. The naming, the human-assigned names, are actually in a hash table that's protected by some locks, and it's just a hash from a name to PID. And I think vice versa. The VM's really complicated. It's also fun to read through if you want. It's not simple, but give it a shot. So how are space systems structured? So that's how Erlang is structured, but how are space systems structured? So this is the New Horizons. It's currently past the orbit of Pluto. So it was launched in January of 2006, and it zipped through the solar system and did a flyby of Pluto in July 2015. It took this pretty famous photo of Pluto on its way out, the heart photo, which I don't know if you've seen, but somebody drew eyes on it and really very happy. Pluto's a pretty devastatingly terrible planet. It is almost as cold as you can possibly get. So New Horizons is so far out in the solar system, you'll notice that it doesn't have any solar panels. That's because the sun at this distance is basically a dim star. So solar panels are effectively a waste. It's not worth the launch cost to ship them up. New Horizons runs on a relatively limited amount of power. It also is so far out that huge antenna dish, it collects all this data, it stores it in memory, scientific data about Pluto, and then it sends it back at 600 bits per second. So it's still sending the information that it collected on its very fast flyby today. And it's supposed to wrap up at some point in the middle of this year. So that's New Horizons, sort of viewed from the outside, but this is also New Horizons. Viewed as a block diagram. So the New Horizons is powered by a radiothermal generator. I said that solar panels were a waste of lift mass, which is true. A radiothermal generator is pretty cool if you've never seen one. It is a tube with radioactive pellets inside. That tube heats up, and then you surround that tube with electrothermal couples. So as that tube heats up, it heats up those electrothermal couples. They generate electricity, and that electricity then powers the spacecraft. The nifty thing is there's too much heat. Now, New Horizons, for instance, its propulsion system has a little catalyst in the bed of the propulsion system that has to be heated before you can turn the thing on. So they just bleed heat off of the tiny little nuclear reaction in the back of the spacecraft into the catalyst beds. Or if you have scientific equipment that has to be warmed up before you can open a shutter, same deal. So it's a tidy little self-contained system. And RTGs are generally used in areas where you don't have access to thermal power. It's one of the odd benefits of the Cold War that we've got a lot of waste plutonium sitting around. And what we've done is decided to put it out into space. For instance, we are littering Mars with radiothermal generators. This is an RTG sitting in the back of the Mars Curiosity, which is an SUV-sized scientific robot that just kind of tools around Mars. So we're particularly interested in the computers subsystem of New Horizons. So there are actually two computer subsystems in New Horizons: the command and data handling, which runs all the radios and interprets all the information that it receives over the radios. It sends information back, and the guidance and control subsystem. So because New Horizons was so horrifically expensive, because you can't go out and repair it if it should fail, each one of these computers is redundant. So there are actually 4 computers, 2 CDNH and then 2 GNC computers. And they're able to detect failures by analyzing the bus. So there's as I understand it, there's a tiny little microcontroller sitting in the middle of each one of the buses detecting signal degradation, and they flip them off. New Horizons is a really weird computing environment. If you're going to get irradiated in the solar system, the first place you're going to get irradiated is in the orbit of Mercury. If you go basically any further in, you're just going to get vaporized, and I don't know if you can rightly call that irradiated. If you want to get irradiated, but you don't want to go near the sun, fly past Jupiter. Jupiter is a pretty radiation-harsh environment, and New Horizons had to do a gravity boost around Jupiter, so it got irradiated pretty hard when it flew around. So the processor inside of New Horizons has to be what's called rad-hard. It has to be able to survive a radiation-hard environment. It runs a Mongoose processor, which is 12 megahertz, and it has a few hundred kilobytes of available RAM to manipulate. Because the Mongoose processor is relatively tiny. It's worth noting that in any spacecraft, especially a spacecraft that goes out quite far into the solar system, this thing was launched in 2006, which means that it started being designed in 2000-ish. Space people are pretty conservative, so a cutting-edge processor in 2000 wasn't going to be something that they would fly. They would fly something that would be 10, 15 years old. So really, any time that you deal with space equipment, you're looking into the past. My understanding is that now Johns Hopkins Applied Physics Laboratory built New Horizons. Now they've upgraded to something that's a couple hundred megahertz processor in any new thing that they fly. So the power constraints on New Horizons are particularly tight. The craft is powered by a single RTG that only gives you 200 watts. New Horizons is unusual in that it has such low power capability. But this means that the software that runs in the New Horizons has to be very power conscious. The software really controls everything. It manages all of the different hardware requirements. Each one of the pieces of hardware send real-time streams of telemetry over buses, and then the computer system evaluates that, and it either executes a sequence of commands. So if you're going to interact with New Horizons, what you do is you have a little packet of information, you ship it to it over the deep space network, you wait for the speed of light to hit that spacecraft, the spacecraft receives it, and then interprets it, which if you squint real hard is message passing. We can't go out and fiddle with the memory of New Horizons, but we can send it little packets of computation and then require that it operate on them. And that's a common setup. Hubble Space Telescope is the same way. You send it a little packet of information, and then that causes the onboard computer to fiddle with the actual hardware. New Horizons is also able to detect faults in itself, generate a beacon tone, tell the human operators that it needs some work, or go into safe mode. And safe mode for New Horizons is pretty fun. Safe mode for any spacecraft is pretty fun. It can't come back for repair, so they have to point themselves at a well-known spot so that we can interact with it. So safe mode for New Horizons is either Earth safe or Sun safe. Sun safe is the least preferable, as I understand it, because there are fewer opportunities for pointing the deep space network at it. Earth safe is the best. But that means that even in a degraded state, the New Horizons still has to be able to do orbital computations to figure out where in the solar system the Earth is, because it has to keep pointing at the Earth. You have to understand that New Horizons is flung out of the solar system. It's achieved solar escape velocity. So it's important for it to be able to, even with it's deviated by gravitational perturbations, to be able to point at a well-known place. If you kind of look here in the guidance control system, there's star trackers, so it's able to point a telescope and then read the stars to determine its position in the celestial sphere. Inertial measurement unit, so it can detect its deflection. It's a really complicated thing, and it's run by a 12 megahertz processor. So an even more primitive computer that I'm very fond of is the Apollo guidance computer. And I've talked about the Apollo guidance computer a lot. It was a computer that was designed in the 1960s. It was pretty advanced for the late 50s. And it was flown in the late 1960s to the moon. The thing that I want to point out, real-time environments are very strange in terms of time. So in Erlang, we get this very nice high-level time facility, but machine-sympathetic environments have to actually deal not with time so much as interrupts, and that's what I want to focus on. This is a view of the Apollo guidance computer's interrupts in 1 second. There are 6 different timers, or interrupt timers. The first 2 are mission time. So the Apollo guidance computer had 14 data bits in any word, and these timers fill registers in memory. So if you, as the software engineer, want to know what time it is, you have to poll 2 registers. So the first time is time 1, and you'll notice that time 1 is actually lower in the list than time 2, and there's a reason for this. Time 1 fires every 10 milliseconds, and if you sort of do the math in your head, that means that the word that it fills up in memory will overflow periodically. And it overflows up, so it overflows into time 2's register, which if you sort of do the math in your head means that the total clock time for the Apollo guidance computer before it wraps around to time 0 again is slightly less than a month. But that's okay because the Apollo guidance computer really only needed to be on for 2.5 weeks. So the second type of time is the wait list. So the operating environment of the Apollo guidance computer was written in machine language with abstraction built on top of that. The wait list are simply low-level routines that the computer needs to do. It periodically needs to listen to buses. It periodically needs to swap some bits of memory so that you can receive command telemetry from the ground. And that's what the wait list does. And it's written in the lowest, most hateful machine language available to the programmer. Time 4 is T4 rupt. Which fires every 20 milliseconds, and this is for synchronous I/O processing. So if you're an astronaut inside of the Apollo guidance computer, you're very tiny, inside of the Apollo spacecraft, which are still tiny, they had to be short men. If you're in the Apollo spacecraft and you flip a toggle or you press a button on the diski, which is the more direct interface to the computer that the astronauts had, you have to wait 20 milliseconds for one of these timers to fire. And this is just a periodic pull of the computer. So the Apollo spacecraft was fly-by-wire to free up the astronauts to do actual science instead of just flying a tin can to the moon and back. The computer would be commanded to hold certain attitudes, to perform certain functions. But the computer had to know that it had been commanded to do that. One of those commands was the digital autopilot, or the DAP. And the DAP has its own interrupt that fires every 20 milliseconds, so that the 20 milliseconds to 120 milliseconds, I should say. This timer is programmable. So the software inside of the, running inside of the Apollo guidance computer is able to say, I need the digital autopilot to kick on in 40 milliseconds, and then the digital autopilot would do so, and then it would compute what needed to be done. So if the astronaut commanded the computer to keep a certain attitude or to do a certain burn so that you could inject into lunar orbit, the digital autopilot would manage that. It was possible for the astronauts to avoid the computer, although they preferred not to. The digital autopilot, 20 milliseconds to 120 milliseconds, is a long time if you're exposing hydrazine in a combustion chamber to the vacuum of space. So the digital autopilot actually has a finer clock that it can program. Pardon me. And that's called the fine scale clock. And that's a sub-millisecond timer. So if you need to fire an engine for, say, just 10 milliseconds, then that's what the fine scale clock would be for. So time in a real-time computer is very strange. There is no concept of time. There's concepts of counters driven by certain ticks. And that's how time works. And we can build time over the top of that. Even in our own personal computers, we've really tricked certain types of crystals that are vibrating at a certain rate to act as time. And they just perform interrupts. So if you've ever built an operating system, pardon me. If you've ever built an operating system, one of the first things you have to do anything interesting is build an interrupt handler. And that interrupt handler is just the thing that handles these ticks. And real-time computing environments expose that as a first-class citizen. And the neat thing about the AGC is that many of these timers were programmable. So it was possible for software to manipulate the rate at which these things ticked. The wait list, the T4 rupt, and the fine scale clock. So if someone was pressing buttons on the diski, the T4 rupt would be programmed to fire more rapidly so the astronaut didn't get frustrated. And if you've never seen inside of the lunar module, the interface to this computer is pretty crazy. This is the interface to the computer. It's also the spacecraft. The astronauts were simply trained to know what these would do, but the computer is responsible for interpreting every switch of every toggle and every program that gets entered on the diski, which is this lovely device right here. The other interesting computing environment is relatively newer, and these are CubeSats. So CubeSats are a new development. They are small, and because they're small, they're relatively lightweight. The primary cost of any major space endeavor is actually just getting it out of Earth's gravity well. If you're out of Earth's gravity well, you're halfway to anywhere in the solar system. So CubeSats are an approach to work around that. They are, the smallest one are called 1U CubeSats. They are 10 centimeters by 10 centimeters by 10 centimeters internal volume, and 2 kilograms or less is my understanding. CubeSats are also neat. Because they're so small, because they're so cheap, it opens up space opportunities to universities, to particularly rich individuals, or sub-organizations inside of space agencies that want to put a thing up for a couple of months. So New Horizons, I think, cost around $550 million, and a CubeSat launch will set you back a cool $100,000, not including hardware costs. But the hardware is actually pretty cheap. Because CubeSats are basically disposable, they just burn up in Earth's atmosphere, they're off-the-shelf hardware. So on the left-hand side, you have an Earth-sensing CubeSat, which has a pretty nice camera in it, and then off-the-shelf hardware boards. Then on the right-hand side, you have a 3U CubeSat, which is 30 centimeters by 10 by 10, meaning that you have more internal volume, you can do more complicated space stuff, you can fit more batteries in, which is an important consideration. But it's still off-the-shelf hardware. NASA even had a series of CubeSats called PhoneSats, which were exactly what they sounded like. They just embedded an Android phone inside of one of these housings and then launched it up. This means, of course, that your computer is not rad hard, but if you're inside of low Earth orbit, you're within the Earth's magnetosphere. So you're relatively protected from solar radiation. So if you flew one of these things past Jupiter, you'd have a real bad time. Actually, you'd have a dead hunk of metal. But you're actually flying these things in low Earth orbit, so who cares? The other neat thing about CubeSats for private organizations, it's off-the-shelf hardware, so they're easier to program. Because they're so light, you can test them. You can test them in production by sticking them on the bottom of a helium balloon and lifting them up out of the atmosphere. And you get a sense of how your batteries will behave. One of my favorite defects is when people put a lithium-ion battery up that isn't space-rated, and they expand and then pop the housing, and then your CubeSat flies apart. There are a couple images of that happening from lower-end lift agencies. So basically, if you have enough money, you can go to anybody that has a rocket and say, I want to put a phone into orbit. You've wasted money, but you can absolutely do it. The Indian Space Agency has done something really interesting recently that lowers the cost of CubeSats. In February of this year, they launched 101 CubeSats from a single fairing. So it's a shame that there was nobody around to look at it, but the fairing would have popped off. That aerodynamic cover that you see there at the top comes off once you've started doing your gravity turn. But then it would have just been like seeds coming out of the housing. But these were all satellites for Earth sensing purposes, for lunar sensing purposes, running on trial runs. Now, because CubeSats are so small, you don't get the best equipment. This is a photograph of Western Australia, and if you've ever seen photographs of the Earth taken from space in the 1950s, this is about the same quality, but it's color instead of black and white, and it wasn't taken by a man in a can. The particular spacecraft that took this was the Vermont Lunar CubeSat, and it had a relatively long life. It flew from November 2013 to November 2015, which is 2 years. It got a free ride up from NASA, and its class, the other CubeSats that it went up with, 83% of them failed. But this one operated for 2 years, and it would have kept going had it not slammed into the Earth's atmosphere. The thing that distinguished the Lunar CubeSat is that they use a programming language called Ada Spark. So if you've never programmed in Ada, you probably also not worked for the Department of Defense. Ada was a programming language invented by the Department of Defense, meant to be used for avionics, satellite systems, things like that. Spark is a subset of Ada that disallows dynamic memory allocation. It takes the runtime checks that are available in Ada and turns them into compile time proofs. So you're able to build relatively safe systems. And the software programming for this was done by university students working in Ada Spark. Most CubeSats are killed by software defects. Yeah. Most CubeSats are killed by software defects. The hardware is relatively easy to do. Most of them are written in C or C++, and they hit unusual conditions, and then they crash. Because if you've ever tried to write a supervisory structure in straight C, you'll know that it's relatively difficult to get that right, especially if you're a second-year university student. So, what problems actually need solving in space systems? If we're going to try and apply Erlang, which has this particular notion of safety, to space systems, we really have to understand what the software systems running in these devices are doing. The first is you need explicit interrupt control. You have to be able to interact at a low level with the interrupts that the machine is sending you. This is, incidentally, this is my very favorite rocket. It is the Delta IV Heavy. If you've ever seen the space shuttle, it's got 3 engines on the back. This is actually just 3 shuttle engines mated to 3 shuttle main tanks. And the 2 tanks on the side just fall off at a certain point. Watch it on YouTube. It's crazy to launch and watch. It seems like it should blow up. On top of this is the Orion D4. So NASA is currently working on a manned mission to Mars. And the spacecraft that will take people there, the crew cabin anyway, is being built by NASA. The service module is being built by the ESA. Orion is going to do a shakedown cruise around the moon, meaning that it'll just go around the moon. Late 2018 is what NASA's been saying. Who knows if they'll be able to keep to that schedule. When the Orion goes around, what they're going to do is release a bunch of CubeSats. So you recall I called it the Vermont Lunar CubeSat, which is weird because it was in low Earth orbit. What they're going to try and do is take that CubeSat technology, mate it to some ion propulsion, and then soft land it on the moon, and then send images back from the moon. Languages also must be able to create and manage real-time computations. So that's pretty native in Erlang. We spawn up a process, and then we spawn a timer at the same time. If that process doesn't signal back to us, we kill that original process. Bam, management of real-time computation. That's actually really tricky to do, depending on your real-time operating system support in C or C++ or Ada. It really comes down to the fundamental operating system that you're running on. You also have to be able to do dynamics computation. So you have to be able to do number crunching. You can build a special purpose ASIC to do these things for you, but that draws power. So maybe you want to use spare cycles in the general purpose computer to do these computations, which is what almost everybody does. The space shuttle had special purpose hardware inside of the GPC to facilitate orbital computation. The GPC was the general purpose computer for the shuttle. We now just call those floating point units. The last thing that you need is, or not the last thing, but you also need fault tolerance. So this is the Mars Opportunity down there in the lower right-hand corner. The Mars Opportunity developed a really fun problem. One of its engines on its wheels burned out. So the Mars Opportunity now has to be driven backward because it has to drag that dead wheel. Had the software of the Mars Opportunity not understood fault, had it not understood that it had gotten a mechanical fault, it would have continued to execute its program. If you're going to interact with a Mars rover, what they do is they pass it a message. They send it a little unit of computation, and then the computer that happens to be attached to a nuclear-powered robot executes that sequence of commands. But because of the real-time stream of telemetry, it's able to know, well, I shouldn't burn out the rest of my engines. So now it drives backwards, it drags the wheels, and they were able to achieve that because they had fault tolerance inside of their software system. You have to be able to do multitasking. So you have to be able to operate and do multiple things at once. So this is a high-resolution strip of Pluto. So the New Horizons just streaked right past Pluto. And it had to be able to, at the same time, turn on its camera, start to capture the image, but as it went by, turn itself toward Pluto because it's flying past in a particular arc. If you have a programming language that doesn't really facilitate this or allow you to cope with the interrupts, then you're going to have a bad time. You're going to slam into an object, or you're just not going to get the signs that you wanted. And for some situations, you need extreme minuscule size. So this is the Lander. It was part of the Rosetta project. It was supposed to land on a comet to do a soft landing and then send science back. It only had 30 minutes of battery life. So what it needed to do was land on the comet, unfurl its solar panels, and then start to do some science. Unfortunately, it landed in a shadow, so it quickly died. But this lander is really interesting because it has such insanely low power capability. It runs an 8 megahertz, 8-bit processor. And the reason they used the particular processor, which is the RTX 2010, was because it had the lowest power profile of anything available in the market. This lander also had to be programmed in Forth, which if you've ever programmed Forth, I highly recommend it. It's a stack-based language, and it's a language that's it's barely a language, but it's designed for density. So it crams itself as much as possible onto the available system. So they were able to put an entire scientific package on a couple watt robot that would soft land on a comet and send information back to Rosetta, which would do the beaming back. And a language has to be able to integrate with existing real-time operating systems. So this is Mars Curiosity. It's able to take selfies because it has a boom and it can point the camera back at itself. You can see the boom sort of cut out strangely. That's not because we decided to build a spear robot, even though that's a pretty America thing to do. It's just missing from the photos. It runs VxWorks and C. I believe it's 50,000 lines of C code running in a real-time operating system. And in the back, unfortunately you can't see it, is the really cool nuclear battery. So what languages have actually been used in space? So as I mentioned, Forth. This is a view of the comet, and in that shadow is the little lander that's only powered by solar power, which is pretty sad. Womp womp. Forth is not commonly used anymore for large-scale projects, but New Horizons carries Forth in some of its microcontrollers. The shuttle flying in the 80s and 90s had a lot of experiments that were running Forth-based programs, and you'll see it scattered through most space agencies in weird places. Assembly is very, very common. This listing actually is from the Apollo Guidance Computer Lunar Module landing. And I want to point out a comment in the top that reads, temporary, I hope, 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 temporary, I hope, 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 permit x-axis override. I want to point out that that was not temporary. It landed on the moon 6 times. Go read through the Apollo Guidance Computer software. It's really funny. The comments are really funny. The program to kick the engines on to start to do the landing on the lunar module was referred to, I think, as Program 66. They just had numeric names for all the programs. The software engineers actually had fun names for all the programs. That particular program they referred to as Burn Baby Burn. HalS was a fascinating language. HAL, I forget what HAL stands for, high something language, and the dash S there is the shuttle variant. So this is a language that was invented by NASA for its avionics projects, but unfortunately it really only got used in the shuttle. The diagram that you see below is actually the diagram of the shuttle computer system and all of the buses that connect it to all the avionics hardware. The shuttle ran 4 computers, primary computers, and then an additional one in parallel. They did this complex voting thing over buses, a fascinating computer system. What is of note about HAL is that it baked real-time notions into the language itself. So nowadays we have computer languages that are meant to adapt themselves to the machine. NASA invented a language that was meant to adapt the machine to the language. So if you were going to write HAL support, your computer had to support HAL as well. So from the HAL programming manual, HalS suggests the point of view that real-time constraints are an intrinsic part of the application, i.e. that timing is part of the algorithm rather than something to resolve later. As a result, real-time statements are integral to the language and allow the programmer to express the entire algorithm directly in one place. So what was cool about HAL, if you had a computation that was supposed to last for just 10 milliseconds, you would put it in a block that was just a 10 millisecond block. And then if it didn't execute in that 10 milliseconds. It would cause an exception, and then so on and so on and so on. But it would be concurrently in parallel scheduled with other blocks. And then the GPC would figure out how to schedule these things according to priority and according to time, which I don't know of any other language that exposes that particular style of interruptive priority real-time scheduling other than HalS, which now that the shuttle is grounded is a dead language. C++ and C are king. The Hubble is 100,000 lines, I think, of C code, and you send it a little packet of information. C is very, very common in the embedded space, and most space systems are really programmed by people that just apply what they know, so C shows up a lot. Ada Spark is also not uncommon, especially in the ESA, as I understand it. It fills the same low-level niche as C++, but it has high-level code. It has high-level constructs. It has abstract data types. It is distinctly a language from the 1970s, but it doesn't have backward compatibility with C, so it doesn't have some of those same defects. And like I said, Spark resolves certain classes of memory errors because it simply does not allow you to allocate memory at runtime. And it has a similar method to Erlang in that you define bounds of variables on computations, and then you crash. Spark extends that further by turning those into proofs so you can never violate those bounds. But fascinating language, and I highly recommend that anybody that is interested in building high reliability Erlang systems also go build some stuff in Spark. It's part of the GNU compiler collection, so it's slow to compile, but you can fiddle with it. So with all of that, with space systems, with the languages that have been used, where can we actually use Erlang today? And the first one is CubeSats. You just put up hardware inside of a relatively minuscule fairing, and you can kind of do whatever you want. So the cool thing about Erlang is it runs on relatively small computers. Now, you don't get the nice firm real-time, hard real-time constraints built into the language, but for the most part, there are really interesting papers asking, well, how can we apply Linux in space? And Linux is not a real-time operating system for CubeSat applications. And of the computations needed to be timed in some way, most of them are soft. In one CubeSat application for sensing lightning strikes that go up, they found that only 1% of all the computations they needed to do had any type of firm real-time requirement. So they just launched a Linux computer programmed in Python up into orbit. The other thing is, this is Dear Monde rover. It's a Google X Prize lunar rover on Mars. Anytime you stick a nuclear battery in anything, Erlang is appropriate. Because you have a lot of power. Erlang is kind of a power-hungry language, especially the beam. If you've ever seen why does beam keep all of my processor cores spinning, it's because it's optimized for a certain type of problem. Now, there are things you can do to fiddle with that, but big deployments. I think really where Erlang would shine are private space stations. So Bigelow has an expandable module on the International Space Station now. If you've ever read about the computer systems inside of the space station is a bunch of tin cans linked together by airlocks. Each one of those tin cans has its own individual avionics systems for life support, things like that. There's no one computer system that controls the entire thing. However, if you were to build a space station, either plonk it on the moon or put an expandable one in space, you want a unified programming model, especially if you want field programming, which I think is where in the future something like Erlang could shine. If you've seen The Martian, they have a programmer on board that spacecraft. There was actually talk of having the Orion field programmable because it would be a 2-year trip. So maybe you would take a programmer along to fiddle with these things. Erlang's ability to do rolling releases, to have these high-level real-time constructs in a relatively manageable computing environment, very useful for that. But Erlang needs to change. What can we do to actually change Erlang to help in these environments? And the first and the big one are bounded queues. We really need the ability to say this process can only receive a certain number of messages before it's simply overwhelmed. And I've talked a lot with Peer Stritzinger about that which, if you're interested, he has a lot of interesting thoughts, so swarm him. You know, and the methods that you would take for this to deal with an overwhelmed or, you know, crash sender, crash receiver, crash both, it would change the computation model of Erlang to say that, you know, a message might not arrive. And I don't actually know what the full ramifications would be, but I do know that bounds inside of critical real-time systems are a common need. Priority messages. So right now, messages inside of Erlang are FIFO. I would like to see that broken so that you could send a message that would pop to the top. Joe is shivering. That also changes the computation model. Yeah.
Very unpredictable.
It changes it in very unpredictable ways, yeah. Yeah, then you have the starvation problem. So then you have to do a different type of analysis on your system. And the last thing that I would like to see are programmable schedulers. So this is a situation where the processes have tagged themselves with priority, and then the schedulers are meant to order the processes in terms of priority. So here it's just a simple greater than, and you'll note that they're ordered in priority in terms of running. This is a common setup in real-time systems. The AGC had it, New Horizons has it, where you have processes or units of computation that must run. Joe is saying you should never do it.
I've done it.
Yeah. Oh, he's saying it has horrible consequences. So it's a common setup in these types of systems. It's wrong, he says. So
that's why it's difficult to program these things.
It is very difficult to program them.
Yeah, that's why.
One of my favorite things is when Joe heckles you from the audience because you know you're doing pretty well.
I worked for the Swedish Space Corporation writing software for a satellite. I did it all at exactly the same priority.
Yeah.
Fine. I added priorities to the scheduler queues and things. It went berserk. It went back to moving it all, and it went through Sweden's first satellite.
Yeah. A very famous case of a computer system that had priority scheduling and would have killed people without it was the Apollo 11 lander. Because of a software bug, they needed to keep reprioritizing the engine firing. But the displays didn't update. They got preempted. None of these changes make programming Erlang easier. They just they adapt it more for what people who program these types of computer systems are familiar with. I've definitely, in my work, wanted bounded Erlang queues. It's not straightforward to know exactly what would happen, but when you propose them, you get heckled from the audience, which is great.
But bounded queues you can do with a process that behaves as a queue process.
Yeah, no.
So you can layer it as an abstraction.
Yeah, you can, but then that draws power. Yeah, it's a tricky problem.
I mean, if you want that, you can have it either in the virtual machine or in
Right.
low-level process. Then it's pragmatics from cost.
Right. So obviously there's a further, more interesting conversation back and forth to go after this. So I'll wrap up, and then I look forward to it. Thank you.